talk about the last piece of this diagram, which basically tells us how we can convert any element in the circuit that we have in time domain to the equivalent version of it in the S domain. That is the whole plan. But before we get there, remember, like if we have a circuit and we want to solve it in time domain, to have like some sort of initial condition to be able to solve the differential equation, right? It turns out if I have the Laplace version of the solution, I don't really have to like go back to time domain and find the initial conditions there, because there is always a relationship between the initial conditions, basically the function time zero, time infinity, and this Laplace transform. So let's quickly talk about that and do one example on that, and then move on to the main part of this lecture, which is how we can actually like convert our elements. All right. So let's talk about this theorem, which is called initial or final value theorem. I'm sure you guys have seen it in DFQ class. I'm just going to go very quickly to just make sure that we all know how it's done. So the first one is the initial value theorem. What this theorem tells me is that if I want to know the value of the function times zero, there's a very nice relationship between that and the value of the Laplace transform of it evaluated at infinity. So limit f of t when t goes to zero is the same as limit of s times f of s when s goes to infinity. So if I have the Laplace transform of f of t, I just need to like multiply it by s, find the limit when s goes to infinity, and then I'm done. And obviously I can use like whatever thing that we learned, like taking limits, right? I can say the same thing for the final value. So I have this final value theorem, which tells me if I want to find the value of f of t when t approaches infinity, one way is to compute f of t and then see like what it is time infinity. But if I'm doing the Laplace transform of it, I don't really have to go back to time to know what it is at time infinity. I can compute this limit. This goes to 0 times f of s. In some sense, they're dual of each other, right? In time domain, it goes to 0. In frequency domain, it goes to the s domain, it goes to infinity. Vice versa for the final theorem, right? So they're somewhat like dual of each other, right? And as I just mentioned, whatever theorem that we learned about taking limits, we can apply here. Right? For example, we learned about like L'Hopital rule. You can apply it here. What was L'Hopital rule? Basically, reminder. I want to find limit when x goes to a of some function f of x divided by g of x. If this limit is 0 over 0 or infinity over infinity, this is ambiguous. So we need to figure out a way to compute this limit. And it turns out to compute this limit, we can compute it as basically this limit. When x goes to of x divided by g prime of x. I'm going to call this like L'Hopital rule. Some other rules that we learned, like taking limits. Right? Keep that in mind. If I'm using this L'Hopital rule, I have to have like 0 over 0, infinity over infinity. So if it's, for example, 0 times infinity, which is again ambiguous, I cannot do this. Right? I have to like figure out like some other way to make it like unambiguous. Right? This this is particularly useful when we're trying to find initial conditions in a circuit, right? Whenever we have a circuit, we're always interested in like a function or current or like voltage right at time zero, at time infinity. And this theorem basically kind of tells us those numbers are, right? So remark, this theorem is particularly useful for conditions in a circuit, right? So let's quickly do an example to see how we can actually apply this. And then we'll verify it by finding like the inverse Laplace to see if it actually works or not. So example, let's just say I'm given this Laplace transform of function f, which is 5 times s plus 1 divided by s times s plus 2 times s plus 3. And the question is times 0 is the limit of f of t when t approaches infinity. Right? Theorem. I know if I want to compute times is the same as this goes to infinity times f of s. So I have to multiply this f of s by s. So I have s times 5 times s plus 1 divided by s times s plus 2 times s plus 3. This s and this s cancel each other out. What is this limit? If I look at the degree of the numerator, that's 1, the degree it's 2. And the whole fraction over here is the same as like 1 over s. Right? Therefore, the limit is 0. Right? So this limit is 0. If I want to find the limit of t when t goes to infinity, again, this theorem tells us that's the limit when s goes to 0 of s times f of s. Right? So it is s times 5 times s plus 1 divided by s times s plus 2 plus times s plus 3. Right? And this s and this s cancel. The rest is like very simple. If I set s equal to 0, I have 5 on the denominator, 2 times 3, which is 6. So it is 5 over 6. Right? What I'm expecting is that if I actually find a Laplace inverse and evaluate that inverse at 0 and infinity, I get the same thing. Right? Let's verify it. So let's find f of t, which is the Laplace inverse of s. Verify this. How do we find Laplace inverse? Well, I'm going to look at my f of s. I'm going to look at the poles. The poles are happening at s equal to 0, 2, negative 3. Therefore, there is no repeated pole. So that's the very simple case that we have. So I can write f of s as 1 divided by s plus a2 divided by s plus 2 plus a3 divided by s plus 3. All right? And I know exactly how to compute. Nice. I know a1 is the limit when s goes to a pole, which is 0 over here. times s minus my pole. The pole here is 0, so it's s, times my f of s, right? So it's s times 5 s plus 1 divided by s times s plus 2 times s plus 3. This s and this s cancel each other out. This is a very simple limit. I set s 0, and I get 5 over 6. Right? I can do the same thing for a2. A2 is limit s goes to s pole, which is negative 2. S minus pole, so it's s minus 2, so it's s plus 2. Times f of s, which is 5 times s plus 1, divided by s times s plus 2 times s plus 3. Again, this and this cancel each other out. This is a very simple limit as well. I just need to set s equals to negative 2, and if I do that, that's 5 over 2. Right? Same thing for a3. A3 is limit when s goes to 3. S plus 3 times 5 s plus 1 divided by s times s plus 2 times s plus 3. This s plus 3, this cancel each other out. If I compute it, that's negative 10 over 3. Okay? Therefore, I have a constant, so I know exactly what f of s is. So f of s is a1, 5 over 6 divided by s, plus 5 over 2 divided by s plus 2, plus negative 10 over 3 divided by s plus 3. Now I know exactly what f of t is, right? I can use the Laplace table. So I'm going to use the Laplace table. Find f of t, right? F of t is 5 over 6 ut plus 5 over 2 to the power of minus 2t t is 10 over 3 minus 3t. Is f of 0 then? Well, remember, t is a function that looks like this. That is 1 for all times greater than 0, and that is 0 for all times negative. Right? So this is u of t. Right? So when I'm computing f of 0, what is u of t? It's 1. Right? So what is my first step? That's 5 over 6. How about my second term? ut is still 1. What is e to the power of minus 2t when t is 0? That's 1. So it's plus 5 over 2. How about the last term? It's minus 10 over 3, which is exactly 0, which matches this one that we have. Right? How about the limit of f of t when t goes to infinity? What is that? What is the limit 5 over 6 ut? What is ut at infinity? Still 1. So the first term is 5 over 6. How about the second term? It's e to the power minus 2t times 1. I know if t goes to infinity, this exponential decays and dies down and approaches 0. So this term over here is going to be 0. How about this term? Again, that's just exponential. It's going to die down and become asymptotically 0. So this term is also 0. So if I find a limit, the limit is 5 over 6, which is, again, exactly the same as what we found. So the theorem is actually true. Right? So keep this theory in the back of your head. trying to like solve for initial conditions, we can always use this when you're actually writing down the differential equation and taking the Laplace transform. Okay. So let's move on to another part of this lecture, which is how can we convert the elements in the circuit to the S domain version of them, right? So circuit elements on S domain. Okay. Let's just assume the Laplace transform of V of t is V of S, and the Laplace transform of t is I of S. Right? So just a definition. Right? Let's start by the very first element, a resistor. So let's just say I have the circuit, I have this resistor, coming through it is IT, voltage across it is VT. Hope is to have something similar in the S domain, right? What is the VI relationship for resistor and time domain? It's Ohm's law, right? So I need VT equals R times IT, right? This is an equality. I can take Laplace transform on both sides of this equation, right? So I'm going to take Laplace transform. So I have Laplace transform of Vt equals Laplace transform of times It, right? It's a constant, right? And Laplace transform is a linear transformation. So I can pull that R of this transformation, right? So I can write this as R times Laplace transform of I of t. Have V of S equals R times I of S. What does that tell? Tells me if I go from time domain to the S domain, the value of R would not change at all. I can basically just write it as its equivalent. So if I go to S domain, I'm going to have a circuit like this with value R. This time current through it is IS. Voltage across it is VS. Right? So far, life is good. It matches exactly the frequency version that we had. Life good. Let's move on to the inductor. Let's move on to the inductor. Second element, inductor. So let's just say I have the circuit. Let's just say coming through it as IT. Voltage across it as VT. We're hoping to find an equivalent version of this. What is the VI relationship for an inductor? V equals LdI dt. Right? So I know V of t equals dt. Again, I can take Laplace transform of both sides. I have the Laplace transform of Vt equals Laplace transform of L di dt. Right? Again, Laplace transform is linear. I can pull constant L out. So I can write this as L times Laplace transform of di dt. Now I'm a little stuck. But not really, right? Because I know how to take Laplace transform of a derivative. If I take Laplace transform of a derivative, I have to multiply the Laplace transform by S and adjust it by some constant. So remember, So if I had any function f take derivative with respect to t, the Laplace transform is s times the Laplace transform of f plus f evaluated at zero, right? So we have to adjust that at the value of the function at time zero. So let's plug it in here. So I have L times Laplace transform of derivative, which I know is Laplace transform of I, which is I of S, minus value of I evaluated at zero. Right? So what do I have? I have S equals SL times IS SL zero. Right? What does that tell me? It tells me if I have an inductor in time domain, I can still replace it by its equivalent, which is SL. But to get the same voltage across it, I have to have it followed by a voltage source with value minus L times I evaluated at zero. Right? Because this Vs should be voltage across this L in the S domain. So my circuit in S domain then becomes this inductor, which I know the value of it is SL. Followed voltage source, negative, positive, I naught will be here. This is going to be IS, and voltage across both of these, yes. Look, if I write a KVL here, I have SL times IS minus L I naught. So that's exactly this formula over here. So I can still treat it just like a resistor, but that resistor must be followed by some voltage source, right? Obviously, we need source transformation, right? If I have some impedance followed by voltage source, I can write that as the exact same impedance followed by current source in parallel with it, right? So I can write this using source transformation. This is source transformation. Is this? So I have this part of a circuit that does not change. I still have I of S. I have this SL, which I know the value of the impedance would not change, followed by a current source. What is the direction of the current source? It's downwards, right? So it is my current source. What is the value of the current source? I equals V over R, right? What is V? It's L I naught divided by SL, right? R and L cancel, so it is I naught divided by S. So if I go from time domain to S domain, I can either replace it by this circuit or this circuit. Regardless, it is not just one SL. It's followed by some source, depending on if you want to just leave it in parallel or series, current source or voltage source. Right? So that's good. It sounds pretty nice. We have like something very similar to Ohm's law. So it's not bad. Let's move on to the last one. which is my capacitor, right? So the third one is a capacitor. Again, let's just say I have the circuit. I have a capacitor with value C. Current through it is IT. Voltage across it is VT. What is the I relationship for a capacitor? I equals CdV dt, right? So I know I of t is C dt. Again, I can take Laplace transform to both sides. So I have Laplace transform of I of t equals Laplace transform of C dt. I know this C is constant, so I can pull it out. So I have C Laplace transform of dt. Again, I have a derivative, so I'm going to use the derivative formula for the Laplace transform. So that is C times S of S plus 0. I gotta remember this is a time domain. Right? What does this tell me? This tells me I of S equals C S S minus C evaluated at 0. Right? I can find VI relationship, right? I just need to take this term to this side and divide everything by CS. So given this, S equals 1 over CS times IS plus V naught over S. Right? What does this tell me? It tells me I can still replace my capacitor with 1 over SC. But to get the voltage across it, I have to add another voltage source. Right? So if I go to the S domain, so what it looks like is that I have this capacitor, which I know has the value 1 over SC. This side it is followed by positive negative voltage source, the value of 1 over S. So if current through it is IS, voltage across the whole thing is going to be VS. Right? Again, I can do source transformation. Like this as 1 over SC followed by current source. What is the direction of the current source here? What is it? Upward. So it is upward. What is the value of it? Again, it's V over Z. So it is V naught over S divided by 1 over SC. What is it? The C times V naught. Right? So I know how to basically convert elements into the estimate. But it's still like pretty simple. I still have something very similar to Ohm's law, but to make up for the voltage across it, I have to add some voltage source or current source. Right? So let me quickly summarize like whatever we have, put it in a table so we can always use that table. So summary. Let's just say I have a need here, my relationship here, SIS relationship here. Okay? Let's start the resistor. Let's just say this resistor has value R. This resistor with value R. Current through IT, voltage across T. The relationship between V and I is Vt equals times It, right? So we can directly take this system, nothing changes. So if I have this resistor and S domain, the value is still N, current through it becomes Is, voltage across it becomes Vs, and the Vi relationship is Vs equals times Is. Right? Let's just say we have an inductor. Let's just say the value of this inductor is M. So if I have an inductor with value M, current through It, voltage across Vt, I know the Vi relationship as Vt equals L di dt. I know I can replace this inductor by its equivalent, which is SL, but this must be followed by voltage source with negative positive here. So I evaluated 0. We said we can just use that to source transformation and rewrite this as SL source going with value for S. Right? And the VI relationship is basically this. Vs equals SL Is minus L I naught. So if this is Is, this would be Vs. Right? So to find voltage across this in time domain, we have to find voltage across these two elements together in S domain. Right? And the same thing for the capacitor. So if I have a capacitor, value C, let's just say current through it is It, voltage across it is Vt, and It is C dt. So we can replace this capacitor by its equivalent, which is 1 over Sc, but that's not enough. So we have to have some voltage source followed by that. And the value of this voltage source is Vt, evaluated at 0, divided by S. Right? And because of the source transformation, we can rewrite this as 1 over Sc, followed by a current source that's going up with the value C times V naught. And if I want to write the VI relationship, I know V of S is 1 over C IS plus over S. So if this is IS, if I'm looking for Vt, which is voltage across this capacitor, Vt is voltage across this, the whole thing in S domain. So this is Vs. Right? Does that make sense what's happening? Yeah? So let me quickly give you like a recipe then. We know if we go from time domain to the S domain, these elements can be treated just like a resistor. So all those things that we learned can be applied here in the S domain. And now we know how to just go back to time. We can solve for anything in the circuit. Okay? So let me quickly put together all we learned. So how to solve a circuit with arbitrary sources. And our sources are sine and cosine. We can always use the phasor representation. Right? And that works perfectly. But what if my sources are just something that we don't know, like a constant, like exponential? What can we do? Obviously, we cannot use the phasor because phasor is only defined for sine waves. The answer is that we can always do like Laplace transform. Laplace transform holds true for any circuit that we have, the sine wave. All right? And how do we do this? Well, the first step is to take the circuit from time domain to estimate. How do we do this? We're going to have to take all the elements that we have. If we have sources, we're going to replace them by the Laplace transform of the source. If we have element, we're going to use the table that we have. Replace the elements using that table. So if I have sources, place them with Laplace transforming them. We have for C, we're going to use the summary table to find the equivalent. Let's look at an estimate. I can treat all my elements just as a resistor. Right? So step 2 is the circuit and estimate using your favorite method. KCL, the analysis, mission analysis, Thevenin loops. So KVL, KCL, Ohm's law, voltage or current divider, superposition, Thevenin, and obviously source transformation. I just used that source transformation twice. Right? You can use it too. Right? And as soon as I solve for the current or voltage or whatever the estimate, I know how to go back to time domain just using the Laplace inverse. Right? So step 3, Laplace inverse to convert the solution back to time. Right? It's very straightforward. Let's do an example. Example. Let's just say I'm given this circuit. I have R equals 10K. It's followed by a capacitor, C, which is 25 microfarad. Let's just say my current source is 3 times e to the power of minus t milliamps. Right? The question is, what is the out? Right? things about the circuit. First of all, look at the UT. What does that tell me? It tells me I have a current source with value 3 times e to the power of minus t if t is positive. And as soon as the t is negative, then t becomes 0. Therefore, my current source is 0. What does it remind you of? Isn't it the same as a switch? So that ut function behaves just like a switch, right? Remember ut, t looks like this. It is 1 for all times greater than 0. It is 0 for negative times, right? So what it tells me is that I have a current source with value 3 times e to the power of minus t for all times greater than 0. Now for time less than 0, it's like that source does not even exist, right? So it looks just like a switch, right? That's the first point. Second point, look at this circuit. This is an RC circuit. So I can always write down the differential equation, write KCL on the top now, and try to solve the differential equation. Right? The first function is going to be exponential. So we're going to have to solve the first order circuit with exponential first function. We can always do that. We can always write down the differential equation and then take the Laplace transform of it. That's the second approach. Third approach, which is the easiest approach, is to convert the circuit to the S domain and analyze it in S domain and then go back to time. And that's the approach that we're going to do. So let's go to S domain. To be able to go to S domain, I got to be able to convert every single element that I have into S domain, right? So let's start here. I have a source. Then I use the table. I need 3 times e to the power of minus t ut has a Laplace transform 3 divided by s plus 1. Right? So this is 3 times s plus 1. This is am, right? That I have here is million. Let's go down to the resistor. What is the value of resistor in time in the S domain? It doesn't change. So this I got no issues with. So I have this 10K. How about this capacitor? What is happening to a capacitor? Well, if I have a capacitor with value C, if I go to S domain, S becomes 1 over SC, right? Followed by a voltage source evaluated at 0 divided by S. Right? We know that. So to be able to replace the C, I got to know what voltage across that C is times 0. But remember, voltage across the capacitor is a continuous function. Isn't it? It is. Therefore, V at time 0 is the same as V at time 0 negative. It's the exact same as V at time 0 positive. So I know V at time 0 is V at time 0 plus. It's the same as V at time 0 negative. I don't exactly know what's happening at V t equals 0 plus, but I do know what's happening at time 0 negative. What does this capacitor become? When the steady state condition. So what it means is that my capacitor becomes open. Right? So if I redraw the circuit, I have this open capacitor, which I want to find voltage across. I have this 10K. Right? What does my source look like? is zero because ut for time negative is zero. What is the current source with value zero? It's an open circuit. Okay? So basically, let's start this. Then what is negative? It's zero. So the good news is, if I replace this C by this, I don't really have to worry about this because this becomes zero. Okay? So I only need to replace this by 1 over SC. And we know what C is, right? C is like 25 microfarad. So it is 1 over S times 25 microfarad. Remember, micro is 10 to the power of negative 6. So if I take it to the top as 10 to the power of plus 6, I can write it as 100 times 10 to the power of 4. So 100 divided by 25 is 4. So it's 40K. So this is 40K divided by S. Everybody see it? Yes? Is it clear why it's 40K over S? Yeah? But I'm claiming I'm done. How? Let's find this current here. Can I find this current? Yes? What is the circuit? That's a current divider. I know exactly what this I is. So this I is, I'm going to use current divider. So this I is proportional to this 10K divided by 10K plus 40K over S times my source, right? Which is 3 milliamps divided by S plus 1. Right? Obviously, I can simplify this a little more. Right? I can find a common denominator down here, which is S. And then I can take that S to the top. So I get 10 to the power of Ks divided by 10 Ks plus 40K. The whole thing times 3 milliamps over S plus 1. Right? I can get rid of this 10K by factoring out the 10K on the bottom. I can do that. So the whole thing over here is S divided by S plus 4 times S plus 1 times 3. Right? Right? What is the out then? The out is voltage across this. Right? Remember, if I had this voltage source over here, V would have been voltage across both of them. Right? In this case, it's 0, so I don't really care. But if I had it, it would have been voltage across both of them. Agree? Yes? Yeah. What is the out here? What is the out this? This is 1 over C times I. Right? So it is 40K over S times 3 milliamps S divided by S plus 4 times S plus 1. Right? So it is 120 divided by S and S cancel. I have S plus 4 times S plus 1. Now I know exactly how to write this in time domain. Right? So I can write V out of S as constant A1 divided by S plus 4 plus constant A2 divided by S plus 1. Right? I know A1 is limit S goes to negative 3 S plus 4 times the out, which is 120 divided by S plus 4 times S plus 1. This and this cancel. This becomes -40. Right? I can compute O2, which is limit S goes to -1 S plus 1 times the out of S. If you compute it, that is 40. Therefore, your Vs is 40 divided by S plus 1 is 40 divided by S plus 4. Right? Now we can go back to the table and compute Vt. V out t is 40 times e to the power of minus t minus 40 e to the power of minus 4c ut. So what we're going to do in the next lecture, we're going to do a few examples on this, and we're going to see how we can apply different methods when we're actually taking the circuit to estimate. Does that make sense what we're talking about? All right, I'll see you guys Monday.